Okay. Is my screen visible?
Yes, sir, it is
Sure.
visible.
Yes, sir.
Okay, let's get started. We'll quickly, as quickly as possible, go through the content, and if there is time, then we'll take up problems or doubts you guys have. So before we begin, are there any doubts? Okay, let's start. So these are some general things. As you might already know, syllabus is week 5 to week 8 for the upcoming quiz. Roughly equal distribution. There's no preference for any week or the other. Note that there will be direct GA questions. That is a policy change that has happened this term. Across the 3 exams, total 10% of your grade will be coming from questions which are directly from the graded assignment. So please make an attempt to solve at least these. What we observed in quiz 1 was, despite it being a very direct, easy graded assignment question, the percentage of people who got it correct was very less. I don't remember the exact number, but it was very less. So this is 3 points on the table for you. So
Dari yang gaji ni.
okay, and then yeah, generally MSQ things. There were doubts about MSQ earlier, so I'll clarify once again that even if one wrong option is marked correctly, then you'll be getting 0 points. Otherwise, there is partial credit for MSQ. All right, so let's get started with the content. So the entirety of week 5 to week 8 will be dealing with functions of one variable, by which we mean the domain is a subset of R and the codomain is R. So domain and range both are subsets of R. So a function, as you know, you have learned it in more generality, from any set A to any set B. You know what a function is. Now we are just focusing on the case where your domain and codomain are subsets of R or R itself. Of course, D is called the domain. R, in this case, R is the codomain, and the range is usually, it's always a subset of R. And we'll be looking at one functions, not only one functions, but one functions are relevant in the first 2 weeks because we'll be defining inverses and so on. So what is a one function? It is a function in which 2 different elements cannot go to the same element, f of x1. If it is equal to f of x2, then x1 has to be equal to x2. You cannot have x1 not equal to x2 and f of x1 is equal to f of x2. Very straightforward examples of functions which are not one are examples like the function f of x is equal to x square. A number and the negative of a number both have the same square. So that will not be a one function. A function by definition itself will say that a single element cannot go to multiple elements, but one is the other way. Multiple elements cannot go to the single element. So that is why it is called one-to-one. Every element is mapped to just one element. And that element is not the image of any other element. So this is a one function. And we'll be dealing with graphs for visualization. As a set, it is just x comma f of x, a subset of R2, the Cartesian plane. So that is why we can plot the points and look at the graph. So, and using the graph, if you have an arbitrary graph given to you, a set of points on the R2 Cartesian plane, then there are 2 tests which will allow you to determine whether or not it is a function, and if it is a function, whether it is one or not. So The vertical line test says that if there is a straight line in the Cartesian plane which intersects the graph in two or more points, if there is even one line which intersects the graph in two or more points, then that graph cannot be that of a function. So as an example, let's take this. So something like this. Let's have some other color. Something like this. Can this be the graph of a function?
No, sir.
No, sir.
No,
Yeah. So if I draw a vertical line anywhere over here, for example, what happens? It intersects in three different points. So such a scenario, if it arises, even for one line, then this graph cannot be that of a function. And what is the rationale? It is that if this is x, this if I'm drawing the line at x is equal to x naught, if this is x naught, then all these points x naught comma, let's say this is y1, this is y2, this is y3. So x comma y1 is also there in the graph, x naught comma y2 is also there in the graph, x naught comma y3 is also there in the graph. But you know that, which means that y1 is equal to f of x naught, y2 is equal to f of x naught, y3 is equal to f of x naught. That thing cannot happen. You cannot have a single element mapped to three different elements. Even two would suffice. Then you can take vertical lines where only there are two images, and even that would be sufficient to conclude that this is not a function. Now, for the horizontal line test, also it is. Let's just take an example. Instead, I'll do something like this. Right? Is this a 1-1 function?
No,
Is this
sir.
a function, first of all? And if it is a
Yes.
function,
yes.
is it a 1-1 function?
It's a function, but not
Yes, sir.
1-to-1.
Yeah, because if you see wherever you draw a vertical line, you will see that it intersects it only at one point. But then if you draw horizontal lines, let's say this one, then you have this point. Let's say this is x1, comma, y0. So suppose this line is y is equal to y0. Horizontal lines are of the form y is equal to y0. Every point on a horizontal line has the same y coordinate. So if this is x2, comma, y0, and this is x3, comma, y0. So what does this mean? All of these are points on the graph. And if you have points on the graph, they're always of the form x, comma, f of x. So y0 is equal to f of x3, it is f of x2, it is f of x1. So you have x1, x2, x3, all of them going to the same point, y0. So this is not a 1-to-1 function. So horizontal line test says that if there exists even one horizontal line which intersects the graph of a function in more than one point, then the function whose graph you have drawn cannot be a 1-to-1 function. All right. Any doubts so far?
No, sir.
No, sir.
All right. So the function that we will now take a closer look at is the exponential function. It is defined for positive values of a which are not equal to 1. You could define it for a is equal to 1 also, but if you have 1 as the base and you raise it to any power x, it just remains 1. So it's a constant function. So that is why we exclude it from the definition. But for all other values of a, we can make sense of what is a to the x. For integer values of x, of course, you can say a square is just a times a. And for negative integers, you can just take 1 by a times a times a times a, and so on. And then you can extend this to rational numbers, and then you can extend this to real numbers also. How it is done, the technical thing is not covered in the course, and for this session at least, we'll not be going through that. But there is a way to raise a given positive base, which is not equal to 1, to any real number x, and that function is called the exponential function. In particular, this number e, Euler's number, it's called Euler's number. It is the approximate value is somewhere in 2.72-ish. So that number is, when you take the exponential function with respect to that base, it is called the natural exponential function. This is a constant that arises naturally in many cases, and this is one specific thing that you will just take note of. And yeah, so now properties of the exponential function, of the graph or of the exponential function itself. So the graph of the exponential function behaves differently when you restrict the base to these two intervals. Yeah. So when it is between 0 and 1, when the base is between 0 and 1, the range is positive. The y-intercept is 0, 1. So let's draw the graph. So as we go larger and larger, what happens to the value of a to the x in this case? Suppose you take 0.1 or so. If you take larger and larger values of, so 0.1 square, for example, is 0.01. If you do it to 3, it will be 0.001, and so on. So the end behavior of this is that it goes to 0. That is on the positive side. On the negative side, it goes as large as arbitrarily large. So over here, if I plug in x is equal to 0, a to the 0, this is equal to 1. So that is why the y-intercept is 1. And then you have something else, right? It never reaches 0, but it tends to 0 as we increase the value of x. So this is other things that you can say is that it's a decreasing function of that. What is the difference when I consider a greater than 1?
Increasing upwards.
The range will remain the same. The end behavior gets flipped, and the y-intercept is still the same. So you can verify all these things, but it will go something like this. Once again, it will never reach 0. So this is an increasing function with end behavior as it goes to infinity as we go to infinity, and it goes to 0 as we go to minus infinity. This is the graph of the exponential function for any base. In particular, if you want to look at e to the x, it will lie in this category because e is more than 2.5 and so on. So yeah, these are the graphs of the exponential functions. Now, one thing to note is that we were talking about one-to-one functions earlier. Are these two one-to-one functions? Is the
Yes.
exponential?
Yes, sir.
Yes. Yeah. So whenever you have a one-to-one function, one of the things that you can do is you can find the inverse of it. Before we go to the inverse, we'll discuss composite. Then maybe inverse will come. So given any two functions, we can define not any two functions. There are some compatibility conditions between f and g that are required in order to define the composite of the two functions. And how is it defined? F of g of x means you take x, you apply the function g first, then you will get some real number g of x, and then you apply f on that. Now that is called f of g of x. So what would be the domain of f of g?
That would be all the x of the z intersection with like all the g of x, which should be all the range value of g of x, which should be there in the domain of f.
So first of all, it is a subset of the domain of g, because first we are going to act g on it. But do all points work? No, because I want to apply f on the real number g of x, such that g of x belongs to range of f. You were also saying something similar, right?
Yes, sir. Only the intersection thing I have added.
Yeah, this way also we can describe it. So you can write it as domain of G intersection with those points. That's also fine.
So
that
can
is what
you
is written.
describe what you have written?
Okay, so what is the domain of f of g of x? So when I want to do f of g of x, first of all, if x is not in the domain of g, it cannot be there in the domain of f of g, right? So this is the set of points which belong to the domain of g, such that this delimiter says it is such that g of x belongs to the range of f. So this condition is also required because later on you'll be doing f of g of x. Let's take an example. Where are we? We are here. I'll keep it simple. So let's do f of x is equal to square root of x, and g of x is equal to x squared minus 5x plus 6. Find domain of f of g. Would you guys like to try? Yeah, maybe we'll take a couple of minutes. It's okay. We can spend a couple of minutes on this.
Sir, will we get such questions in the quiz? Like, is there a chance?
Find the domain. You'll not have descriptive questions. You'll have objective questions. Okay, this is possible. Let's say let AB be the largest interval such that f of g is defined on AB. Find b minus a.
Sir, actually the
is-
domain here is 3 to infinity union minus infinity to 2. So if we'll just take the minus of that g of x, then it would be
Okay. Yeah.
b
Yeah.
minus
Sorry.
2.
Yeah. You're right. You're right. Let's do this. Yeah.
It would be 1.
What are the
I'm
guesses?
getting it as 1.
1.
So how do we go about doing it? First of all, let's see what the domain of each of the functions is. The domain of G is R. In order to, I'm looking at largest possible domains. You can have any smaller domain also as the domain of G, but the largest possible domain for G is R. The quadratic polynomials can be evaluated at any point that you like. And what is the domain of F?
R plus
Positive reals.
including 0. Yes.
Right? 0 to infinity, closed at 0, the interval. Now, if I want f of g to be defined at some point, I'll be looking at stuff like, so first there is no hurdle in, at the first step, there is no hurdle. G of x can be defined. But what happens is you're going to do f of g of x. So this g of x needs to be in the domain, as we had stated earlier. Meaning what has to happen? Minus x squared plus 5x minus 6, which is g of x, has to be greater than or equal to 0. Why? Because g of x should belong to domain of f. What is domain of f? It is 0 to infinity. So g of x has to be greater than or equal to 0. But what is g of x greater than or equal to 0? So here, if you want to do it analytically, that is also okay. If you want to appeal to the graph of the function, what is the nature of the graph of a quadratic function? It is either
Parabolic.
it's parabolic. So is it pointing downwards or upwards? It's opening upwards or downwards?
It's a downward because
Downward.
A is negative.
Opening downward as A is negative,
Yeah.
leading to
So,
equation.
right. So it's negative. So it's something like this generically. So what I need to do is, in this case, it will actually be something like this. But what I need to do is find these two zeros of the thing. And in between the zeros, I have the function to be positive. So what are the zeros of this? What are the roots of this quadratic equation?
2 and
So
3.
2 and 3.
So this is this correct? Minus, yeah, this is okay.
Yeah.
Yes, sir.
Yeah, this I've just written as this. So directly from here, you'll know that between 2 and 3, you're good. So largest possible domain is this. But if you want to do it analytically also, you can do. If you want the minus of this expression to be greater than or equal to 0, this has to be less than or equal to 0.
Yeah, it will be.
Which means x minus 2 is this and x minus 3 is negative, or you have x minus 2 to be negative and x minus 3 to be positive. So case 1 is x is greater than or equal to 2 and x is less than or equal to 3. which is what we had got earlier. But then the other case also we have to settle. So you need x less than or equal to 2 and x greater than or equal to 3. Does there exist any x which satisfies this condition?
No, sir.
No. So this is, in this case, there is no x, but then we have this case which survives,
Yes.
2 to 3. And then what, because the
B
question is
minus A
objective,
will be 1.
so this is correct. This is fine. This is still maybe simple. I could do something like 1 minus x. F of x is 1 minus x, and then g of x is this quadratic function. So when you do things like that, it'll not be just finding the roots of this, it will be finding the roots of a quadratic equation with possibly different coefficients, constant term, maybe things like that. But this is the idea is clear, right? What
Yes,
needs
sir.
to be
It's
done?
clear.
Yeah. And you don't even need to know the function. If I just say the domain of f is something like 0 to 1, even then you should be able to find it. Without giving f, so take this as an exercise maybe. Take g as the same thing. F is a function whose domain is 0 to 1, something like that. Then find the domain of, or from an exam point of view, you'll get some number that needs to be calculated, which will be very immediate after you do domain. It's not much different. You'll have to just look at points where it goes to 1. Probably this function doesn't even, what's the maximum value of this? 5 by 2, 2.5. Okay, you can check that. But yeah, the point is that you don't need the explicit expression for the function also. You just need to know what the domain is in order to compute the domain of f of g.
0 less than or equal to x minus x square plus 5x minus 6, that method, sir?
You can just have,
So g of
you'll have
x
to,
should be between 0 and 1.
yeah. You can do this and simplify this and get the
Sir,
interval. Yeah.
in the previous question, can you just tell me how you found from that step x minus 2 is greater than equal to 0 and x minus 3 is less than equal to 0?
So
Can you
did
just,
you understand how we got this
yeah,
equation,
yeah,
this
yes,
inequality? Yeah.
yes.
So in this inequality, we have a product of two numbers, which is non-positive, which is less than or equal to 0. When is a product of two numbers negative or non-positive? One of them has to be positive and the other one has to be negative. So we take two cases. Case one is the first number is positive, the second number is negative, and the second case is, this is or. So one of the two cases, if you
Okay,
have
okay.
any one of, so the
Yeah,
second case is the first number is negative and the second number is positive.
okay.
So the second case does not give rise to any numbers because you need less than 0 and greater than 3, which is an empty set. But the first case gives you what you require.
Yeah, okay. Thank you.
Right? So this is about the composite functions computing the domain of a
Hello, sir.
composite function. Yeah,
Sir, in the second example, can you scroll down
yeah.
here only? So, like this inequality less than equal to
Mhm.
1. So here, I'm getting some kind of complex roots for x. So there will be no such x for which, I mean, here the
Why are you
domain,
getting complex roots?
because x square plus 5x minus x square minus 5x plus 7 is greater than equal to 0 while
Can you
solving
scroll
the
better?
right inequality. This,
So even, yeah, okay. This part gives you 2 to 3
this
itself,
part,
right?
yes, this part,
Can you
Okay.
scroll below? Up?
and
Right,
the
we know.
right part is something like it
X
will
square
Yes, sir.
minus 5x. What else do we have? Plus 7, is it?
yes, sir, exactly. So D
Plus
is
7
basically less than 0 here.
less than or equal to 0. Okay.
Yes, sir.
And what are you saying?
Sir, here the discriminant is less than 0.
3 square minus 4ac. Okay.
So what can we say about this thing? Will there be any x which should be there in the domain?
It should be, as in, even if I just substitute 2 or 3, you should be getting the thing.
Axis of symmetry is point like 2.5 here. So we'll just stop for.
Now, what's the problem?
I mean, what will be the answer for this, sir?
You
So
want it to be less than or equal to 1.
even if you take, yes, sir,
At 2.5, what happens to this function, g of
this
x?
is the vertex, the x coordinate of vertex. So
Plus 5 into 2.5. What's 5 into 2.5? 125. 12.5 minus 6. So in this case, the vertex is itself 0.25, right? So
yes, it will always be positive.
no, this function has this thing at 0.25. So if you want your f of g to be well defined, this thing is between 0 and 1, that is fine for me. Now, in between 2 and 3, the function is g is greater than or equal to 0, that is satisfied, is less than or equal to 1 also is satisfied, because 0.25 is the maximum value that it takes.
0.25 is the maximum value. Okay. Okay, sir.
Is it not?
Uh,
It's 5 by 2, wait, negative 5 by 2 square plus 5 times 5 by 2 minus 6.
sir,
So
plus
that's
7
minus.
you should take, right? Because
No. I'm just looking at g. In
okay.
what
For
is the value of g in between 2 and 3? It is positive, we know. It is non-negative, that we know. And it is, what is the maximum value it takes? That is attained at 5 by 2.
yes,
So
sir.
I'll get minus 25 by 4 plus 25 by 2. So I'll get plus 25 by 4 minus 6. Yeah, what I was doing earlier was correct. So the maximum value of g is 0.25, which is well below 1.
Yes. Okay.
So in between 2 and 3, g of x will lie in 0 to 1. That is there.
Oh, okay. Okay. Okay, sir.
Okay. Now I understand your confusion because of the analytical thing. We are doing something wrong. What is it that we are doing?
Sir,
I
actually, I
want.
was solving this by solving the inequality. So
Oh, okay.
in
It has to be
that way.
greater than or equal to 0, right? Then this is fine. Now, okay. So this, if you're not looking at the graph, and if you just look at the equations, inequalities, and the conditions that follow, this part of the inequality gives you uh, 2 to
2 to
3
3.
as
Yes.
before. Now, the second part of the inequality gives you this condition, right?
Yes,
X
sir.
square minus 5x plus 7 is greater than or equal to 0.
Yes, sir.
So what is this quadratic equation? It is a parabola which
Upward
opens
facing.
upwards.
Yes, sir.
So and it has no real roots. So that's always positive.
And between 2 and 3, it will also be positive. That's why the domain will be 2 and 3, right?
Yes. So
Okay.
it is 2 and 3. So this doesn't give you any restriction. So this inequality is satisfied by any real number.
Okay, okay.
Okay, so you want this equation to be satisfied and this inequality to be satisfied, both inequalities to be satisfied. So you need x in 2 to 3 and x in R.
Yes, sir.
So you have to take the intersection of the two, which is just 2 to 3. It's fine.
Yes, sir. Yes, sir. Okay.
If you can
Now,
explain, like the domain of Gx is becoming 2 to 3, that is fine.
so that is for this, right? This
Inner function.
so
Yeah, inner function.
yeah. What part do you want me to explain?
So f is a function whose domain is again 0 to
Okay,
1.
so you want okay, let's take this up more closely then. So if f is a function whose domain is 0 to 1, I want to find the domain of f of g. As we were saying earlier also, the domain of f of g is the set of points such that, let me write this later again. You want to find x such that g of x belongs to domain of f. So this is the requirement for a point x to be in the domain of the composite function. Domain of f is given to be 0 to 1. So I want g of x to be in 0 to 1. And I know I have the explicit expression for that. So this is what we have to solve. The set of all x which satisfy this inequality is what we have to solve. Is this fine? Is this part fine?
Yes.
So
Yes, sir.
then we have two inequalities, two parts of the inequality. One requires that this has to happen. And I also need the other part of the inequality to be satisfied, which is this. Now, what is the set of points for which this inequality is satisfied? That we have already seen over here. That happens to be exactly 2 to 3. So you need x belongs to 2 to 3. And what is the set of all x such that this inequality is satisfied? If I rearrange this inequality, what I will get is x squared minus 5x plus 7. I'm taking the 1 to the other side and multiplying by minus 1. I need this to be greater than or equal to 0. All right, until this is okay for you.
Yes.
Now, if you try to look at the roots of this equation, you will see that it doesn't have any real roots. B squared minus 4ac will be 25 minus 28, which is minus 3. So this doesn't have any roots. So what does it mean when a quadratic function doesn't have roots? It's either entirely positive or entirely negative. But if you look at the quadratic equation, what do you think it is? Is it entirely positive or entirely negative?
Positive.
Positive.
If you want, you can just put candidate x equal to 0, you'll get 7. So if it is positive at one value, it is positive at all other values. Or you could appeal to the coefficient being positive, so it's a opening upwards parabola. So everything is
You
positive.
can see the vertex is 5. So x is 5.
But this is
5 by 2.
2.5.
Yeah.
Yes, 2.5. Correct.
Yeah. So this inequality is satisfied by all x. This actually doesn't really put any condition. This is satisfied by all x, but we want this and this to hold. So what are the set of values, set of real numbers which for which both the conditions hold? Is exactly this, because this is kind of a vacuous condition. It is not imposing anything new.
Mhm.
So you're doing the intersection of these two sets, which will be just the smaller set, because that is the universal set itself. Okay.
So
Is
for
this fine?
second equation, negative values will not be the solution. So how x is an element of R, it should be R plus.
No, you can have test it on -1. What about x is equal to -1? You will get 1 plus 5 plus 7, which is also fine. I want that
Yes, yes.
expression to be positive. I don't want x to be positive. So if you look at the graph of this at 5 by 2, somewhere 2.5, you'll have the vertex, but then it is opening upwards, meaning irrespective of what value of x you take, f of x is going to be positive. F of x being this, now f we have already used, this quadratic function is positive.
Yes, understood.
So this condition that the quadratic function has to be positive is satisfied by every real number.
Yes.
Okay, so this inequality is redundant. It's not contributing any constraint. So the only constraint is this. So suppose if you are in some problem, if you get something like 2.5 to 4 or something, for some reason, if you get something like this, you can probably come up with a good example where this happens, but right now I'm not going to do that. Then when you take the intersection, your answer will be 2 to 2.5, if such a thing happens. Okay. In this
2.5
case, it
to
has not
3, that should be right.
Right, 2.5 to 3. Yeah, correct.
Yes.
So to take the
So-
intersection of the two,
Yes, 2.5 to 3.
so if you want, you can take this exercise star instead of 0 to 1, you take 0 to 0.125, because I know the maximum value of the function is 0.25 and I don't want to go until then. So you can take this as the domain of f and solve this for yourself. And you will get something else. You will get a union of two intervals, two closed intervals, the exact values of which I'm not going to compute now. But yeah, try to do this. If you can't get it, you can write to me later also. But is there a doubt?
No, actually, I just wanted to ask, out of both the methods, the graphical one and the one which we use right now, which one is better in exam point of view, which saves time?
That is actually up to you. I would, some people find it, visualizing things as easier, and some people find just solving the inequality easier. That is your choice. Whatever works faster for you.
Okay. And is it possible that f of g does not have a valid domain? I mean, is it possible that f of g will not have a domain?
Yes, f of g is not defined at all. That can happen if you take.
Here in this case, if you take this x square minus 5x plus 7 less than equal to 0, then the intersection part
Well,
will
that
get
inequality
null.
itself will go away, but you can come up with easier examples also. Let's take. Let me write it inside some box. We'll take the same thing, root x as earlier, and g of x as
Minus of root x you can take.
wait, just 1 moment. I want square minus x squared. Something like this. This is trivially it will be negative. This
Yes,
g of
sir.
x will always be negative, right? Because x square is a positive number always, non-negative number at least. And then minus of x square is a non-negative number. Minus will become a negative number itself. So can you define f of g?
No.
Yeah,
No.
you cannot define the graph of uh, you cannot define the square root of negative number. So within
And
real
f of
numbers, you
g
cannot.
cannot be a imaginary number, right?
Yes, we are not dealing with that. Of course, there is theory of complex numbers. That's not part.
Okay.
All right. So yeah, that's that about composite functions. Now, as I was saying earlier, whenever you have a one-to-one function, you can compute its inverse. What is the inverse? If x goes to f of x, then you can define a function from the range as y goes to f inverse of y or x goes to f inverse of x. The x or y, whatever you use, doesn't matter. But what it essentially does is that it maps it. The domain for the inverse is the range, and the image of any element of the range is its pre-image with respect to the function. Best way to see it is draw your function like this. If x goes to f of x, this is the forward function. So the inverse function just takes f of x to x and for each element. Now you see why this injectivity was important. If you have something like this, you cannot define the inverse, because when you define the inverse, this element, for example, will have two images, because the image of the inverse is actually the pre-image with respect to the original function. So, but as soon as I have one-one behavior, even though it might not be surjective, we are not defining the inverse on the codomain. We are defining the inverse on the range. So that is how inverse of a function is defined, and it satisfies this condition that f inverse of f, the composite function f inverse of f, is the identity function. Identity function is a function from a set to itself, which takes whose image is the same as the input. All right. So range of f is the same as domain of f inverse.
Okay, sir.
All right. So
Sir, in some questions, let's say we are asked to find the range, and if that function is one-to-one, we can like it. Let's say it is very difficult to find the range just by seeing the question. Then we can, in that case, if that is one-to-one, we can find the inverse, and we can find the domain of that, right? To find the range
I
of.
don't think it will be any easier that way. Will it become easier?
Uh, uh, like just by looking at the function, if we are not able to find the range, can we find the inverse first, and we can find the domain of that inverse, and that
It's perfectly fine. It's correct. There's nothing mathematically wrong with it, but I'm not sure in what scenario it will actually be easier.
okay.
Let's say you have something
Excuse
like
me.
this. Now, what is the domain of f?
R minus minus 2.
What is the range of this?
Yes, sir. That is what uh, I want to know. Like, can we find that by inverse method?
Let's say y is equal to f inverse of x, and then you'll have x is equal to y minus 1 divided by y plus 2. Rearrange xy plus 2x is y minus 1. What do I want? I want y. So 2x plus 1 divided by 1 minus x This is f inverse of x. And you're saying the range of this is r minus 1. So that is the domain of f inverse.
Yes, sir, exactly. In this way.
Or the domain of f inverse is equal to the range of f. Yes, but how are you guaranteed that this is an injective function? Can you just look at it and say it's an injective function?
We can check that by f of x1 equal to f of x2 method.
Use it,
Mm,
but then you'll get a lot of well, if you don't have an injective function, you can't compute the inverse. Like you'll run into some problems when you do things like this.
Yes, sir.
So,
No, sir.
so
What I was saying is, if we know that the function is 1 to 1, can we find the
Mhm.
range in this method?
Yes, you
Okay.
are. So what are you doing? So when you compute the inverse, you're saying let y is equal to f inverse of x, and which implicitly assumes x is in the range of f, right? And then you solve it and you get y is equal to something. You cannot have x equal to 1, right? Because if I start out with what is f inverse of 1, I want to check what f inverse of 1 is. If I go and do this computations, I will not get any value of y corresponding to this that you can check. We'll get 1 is equal to minus 2 or something like that.
Yes, sir.
So it is doing the same thing in the background. You can do this. You can use this.
Okay. Okay, sir.
All right. Now, if you have obviously non-injective function, when you try to compute it also, you will have some multiple solutions kind of a thing. So this is fine. You can do this. So as soon as you asked the question, I knew you were going for something like this. This is fine.
Okay. And this is
Yeah.
also 1-to-1 function.
Yeah, this is a one-to-one function. Yeah.
Yes, sir.
So here you can actually see it easily because this is what 1 minus p by x plus 2. Then if you use your 1 by x is a 1-to-1, or if you do f of x1 is equal to f of x2, x1 is equal to x2. Yeah, in this formulation, it is easier to see that
Okay,
it
okay, sir.
is.
How you wrote this in such fashion?
So when you have rational things, you can write it when you have the same degree polynomial, or if you have ax plus b, you can do this,
Okay.
and then you can split it. Right? This I can do. This is just 1 minus 3 by x plus 2. In fact, if you do it this way, is it not clear from this that the domain, the range would not include 1?
Exactly, sir. Because this 3 by x minus 2 uh, cannot be, this can't be
0.
0. Yes.
Yeah, it can't be 0.
Okay.
So if you look at the graph of 1 by x, it will be something like by x, which is positive, positive, or negative. It will be something like this. Are you aware of the graph of 1 by x?
Yes, sir.
Yeah, so it's something
It's
like this.
hyperbola.
So the range of that is what? It's just everything other than 0.
Yes, sir.
So 3 by x plus 2 is very similar. You're just shifting it by shifting the input variable. So, and then you're scaling it. So it will still miss 0. Of course, you can verify it directly also, but that's also the graphical idea is that. So this is one more way of looking at it, but this is perfectly fine. If you can find a value of x such that f inverse of x happens to be a real number, then that is of course in the range. So this is okay.
Okay, sir.
Okay.
Sir, will you be sharing this PDF?
Yeah, in the same folder as always, we'll have in the same sheet as always, we'll get this.
Okay, sir.
Where were we? So coming back to exponential and all that, exponential function. This, we saw that the graph is something like this, even if it is not e to the x, even if it is a to the x, it's either like this or like this. Both of these happen to be one-to-one functions. It's a monotonically increasing or monotonically decreasing function. So increasing or decreasing functions are strictly increasing or strictly decreasing functions are very clearly invertible functions. You can find the inverse of that defined on the range of the function. In particular, when I'm looking at exponential function, I can define the inverse of the exponential function with respect to any base. What would be the domain of this? So that inverse of the exponential function is called the logarithmic function. So what is domain of log?
That is basically the range of
this
that
exponential.
exponential, which will be 0 to infinity. 0 is not included.
So this is 0 to infinity. Now, once again, the graph of the logarithmic function has looks different based on just one a to the x. It would split this. Okay. At least natural logarithm looks like this, right? What does the graph of the logarithmic function when a is between 0 to 1 look like?
Increasing function. So, 0 to 1, then it would be decreasing.
Decreasing
Uh,
between 0.
so just the mirror image of this with respect to x.
Oh, it's like this.
Yes, sir.
The exponentials would be mirror image with respect to y, so this will be mirror image with respect to x. Yeah. Anyway, that's not really very important. What is important is to know what logarithmic function means. Now, if I have a to the x is equal to y, this is the same as saying log of y to the base x is equal to the base a is x. This is just using the definition of the inverse again. So what does this mean? With respect to the exponential function, x goes to y. So with respect to the inverse, y should be exponential inverse. No, exponential inverse of y should be x. But by definition, exponential inverse is log to the base a. So this is the most usable and the thing that you have to use, which is something which is natural. So when you say what is the logarithm of a number to the base a, it is the power to which a has to be raised in order to get that number. Right?
Okay,
Now the
sir.
domain, range, Okay, what is the range domain? I had written it down and I erased it. So let's write that again. Is 0 to infinity. What is the range of log?
R.
Domain of exponential. Why is this statement true?
Because these are inverse of each other.
Yeah. So log inverse, so exponential inverse is log, is equivalent to saying log inverse is exponential. So the domain of the inverse of a function, here the function being log, is the same as the range of the logarithmic function. So you will get both of them to be R. As we were drawing earlier, this is something. And what is this point? What is the x-intercept?
That is 1, 0.
Logarithmic function to any base attaches or passes through the x-axis at the point 1, 0. And it is negative before that. It's positive. It's a monotone function. So all of that follows. Now, for most problems, you will be using these properties. And later on in calculus, you will see why such properties, this property will be used to calculate, let's say, derivatives or something of a function. If it is in the exponential form, you can take the log of the function and then bring it to a more manageable form.
So
We
the
have seen
fourth
that
one
in
is incorrect, I guess.
yeah, that's incorrect. So this is wrong. It is minus log. And log a, everything else is fine. No? Yeah.
The quiz 2 pattern would be similar to the quiz 1, like the difficulty level.
Yes.
Okay.
These two things are easy to see, the first and the second one. So what is the power to which a should be raised in order to get 1? That is 0.
0.
That is why log 1 is 0 always. What is the power to which a should be raised to get a itself? That is 1. So the rest, we'll not even give sketch of proof. We just take it as a fact. And this is used to solve what are logarithmic equations. So sometimes you'll get something like log of x minus 1, log of x, something like this is equal to something, and you'll have some base, maybe e, and you have to simplify it using these. Maybe it's just log 3, and this will simplify to a quadratic equation, and you have to solve the quadratic equation. Maybe you'll get 2 roots, one of which will give negative number over here, and that will not be a solution, and only the positive one will work. So, all of these can happen. Maybe we'll take up examples if we go through the content before 10 o'clock. But by now, I'm sure you have done enough exercises of this form. So that is it about exponential and logarithmic functions. The next part, which is week 7 to week 8, involves calculus of one variable, where we'll be looking at functions in general after looking at certain classes of particular functions like the exponential and logarithmic and polynomial functions. Now we'll go to the general case and try to formulate certain natural notions. What we will require very extensively is the concept of a limit. We'll be looking at limit of a function, and that will be used for continuity, for differentiability, all of those things. But before we go to the notion of the limit of a function, first we'll see what the limit of a sequence is. A sequence is just an ordered set of numbers, ordered using the natural numbers. Usually we take n equal to 1 or sometimes n equal to 0 also. So it's just a set of real numbers, one corresponding to each natural number. Common examples are this, all of these are very common examples. Now, why do we look at sequences? Why do we look at sequences? We'll look at it when we are talking about limits of functions. But first, we'll see, using these two examples, what it means for a sequence to converge or not. So, what is the nature of an as you increase the value of n?
Close to 0.
Yeah, I can make it as close to 0 as I want, right? So if I look at a to the power a n to the power 10 to the k minus k, what is this? This is simply 10 to the power minus k. So as I increase k, I can make it as small. I can make it close to 0 to whatever number of decimal places that I want. But it is never going to become 0 also. There are sequences which eventually become the limiting value also. You can just take the tail of a sequence to be this thing. But the point is that if you are talking about convergence, what you want is, after a certain point, all the terms in the sequence have to be close to a certain value. In this case, it is 0. But does the same behavior happen for this sequence Bn?
No.
No, it alternates between either 1 or minus 1.
Yeah, so it keeps going up and down. So it doesn't really converge to a particular point. So this, without making the rigorous definition, we'll just leave it as sequence is said to converge to a real number if it comes arbitrarily close to n. Otherwise, it will diverge. So this is convergence or divergence of a sequence. These are certain rules that you can use to compute certain limits. Like not all limits will be doable like this in general, but the questions that you will get will mostly be doable by this, and certain standard limits that the prof has given. You can go through that. One of the strong results to prove convergence is sandwich lemma, especially when you have bounded functions like sine or cos. You can usually remove that part and only analyze the remaining part. This is also examples in this fashion also we have discussed during summary sessions and solve with us sessions. So I won't go to discuss all those things again. But all of these are very believable rules. Sum of limit, if you take the sum of two sequences, then that sequence also converges, and the limit is equal to the sum of the limits, scalar multiple, product, quotient, exponentiation, logarithm, all of these things. The limits of sequence behaves well with respect to all of these operations. And then there is sandwich lemma, which says if I have a sequence which is sandwiched between two sequences, both of which converge to the same limit, then this thing in between also has to converge to the same limit. It's like if you have, let's say, two sequences, if you have some real number a and you have one sequence like this, which converges to this, and then you have another sequence, whatever it may be, eventually it will go there. Now, if I have this third sequence, which is in between those two at every point, then of course, at the limiting, the behavior as you increase, and also it has to go to something in between the limits of the two sequences. But the limits of the two sequences are the same. So this also should be a convergent sequence, and the limit happens to be the common limit. So suppose this is a, and this is, as per whatever I've written over there, it is Tn. So if Cn is between these two, that also has to converge to the same limit. That is the essence of sandwich lemma. How you use it in problems, you have to solve problems and see. Now, once we have the notion of the limit of a sequence, we can talk about the limit of a function. It might seem convoluted why we define it in terms of sequences, but this allows us to make a rigorous definition in terms of sequences. Now, if I have a function and at some point, let me draw a small graph function. So a, and let's say the graph is something like this. This is f of a. Now, this is obviously a continuous function, continuous looking function. In order to make the notion of continuity rigorous, what we will do is the following. We'll look at sequences of points which converge to this a. I'll take a sequence which is less than a, but converges to a. For example, a minus 1 by n is one such sequence. You can always use this sequence. All right. And now I look at the corresponding function values, where now f of an in general, in this case, I've taken a minus 1 by n. If I take a sequence a n goes to a, f of an is another sequence of real numbers. If that approaches some real number, then we say, of course, f of an converges. Now, irrespective of what sequence I take, if I get f of an to be a convergent sequence and that it converges to the same number, then we say that the left-hand limit of f exists at that point. Why left-hand limit? Because we are looking at the behavior of the function to the left of a. We are considering sequences less than a which converge to a and corresponding function values. Right? Similar notion for the right-hand limit. The only difference being that we consider sequences which are to the right of a, meaning whose value is greater than a, and the sequence has to converge to a. You look at f of a n. If it so happens that irrespective of what sequence I take, I get the limit of f of a n to be r, then r is said to be the right-hand limit. Once again, it is better to work with an example which was already seen, but there's no harm in reading. So f of x is equal to the floor of x. How is it defined? It is defined as the
Greatest
smallest
integer.
integer, greatest integer smaller than or equal to x. Right? What would the graph of the function be? At 0, it is actually equal to 0, all the way up until 1. At 1, it has a jump. Right? This same jump happens at every integer point. And similar thing over here also. Now let us take x is equal to 1. I want to know what limit as x goes to 1 minus f of x is. Similarly, I want the right hand limit also. If it exists, I want to see what its value is. So when I'm looking at the point 1 and I'm looking at the left hand limit, what is it that I have to consider? I have to consider the points which are to the left of 1. So let an be any sequence such that an goes to 1 and an is less than 1. What would f of an be?
0.
Eventually, at least it will be 0. So f of an is 0. Let's say it's just a very small value less than n. It's all within the interval 0 to 1. So f of an is equal to 0, irrespective of what sequence I take. As long as it is less than 1 and close to 1, f of an is 0. So what is the limit of a constant sequence?
The limit of a constant sequence, meaning like.
So if I say an is equal to c for all n, this is also a sequence, right?
Mhm.
So what is the limit of this sequence?
Oh, that would be c.
That would be c itself. So in this case, what is that constant?
0.
So it is 0. Instead of looking at it in terms of sequences, even if you just look at the diagram, if I take a sequence of a sequence of real numbers less than 1, close to 1, such that they converge to 1, the corresponding function values are still 0 itself. And that function sequence converges to 0 itself. Right? But what about, so therefore, I'll call it LHL, left-hand limit, or I've already written it over there. So this LHL is equal to this is equal to 0. But what about the right-hand limit? Limit as x goes to 1 plus of f of x. For this, I need to consider points which are to the right of 1, which approach 1. For whatever sequence I take, what is the function value going to be?
1.
1 only.
So if I have an goes to 1, an greater than 1, then f of an is equal to 1. This is once again a constant sequence. So limit as n goes to infinity of f of an is simply 1. So in this case, what happened was we have both the left-hand limit and the right-hand limit to exist. They're not equal, but that we have not talked about yet. This is just telling you how to see or how to compute the left-hand and right-hand limit. Now, of course, if you want to talk about continuity, one thing that you have to avoid is jumps. This is clearly a discontinuous function. There are very obvious jumps at the integer points. So the formulation of continuity comes with the notion of left-hand limit and right-hand limit. We are in a place to define what is continuity. Before that, you have properties of limits. Properties of limits is, once again, sums of limits behave in a good way, scalar multiples, products, quotients, and
Sir,
sandwich
I
lemma.
have a doubt.
Yeah.
Sir, in the function
In
that you
this,
have made, the graph
okay, this one is it?
mod of
Yeah,
x graph. So
not
this
mod
function
x.
is
This is
discontinuous.
floor.
What?
Yeah, this is the floor function. Okay.
But you're calling this function, and in the first lecture of week 5, it was said that when breaks are there, then it's not called a function. Breaks in a graph doesn't mean function.
No. For a function, it is fine. It is not called a continuous function.
But there was only 2 criteria. It should not have any sharp vertex and it should be continuous. Then a function is called a function.
No. I'm sure that is not
So
the
it
case.
can be called as the step function, right?
This is a step function. It is a function. So for a function, all you need is that every element of the domain is mapped to a unique element in the codomain. So what is it that you're referring to where you don't need
Lecture,
you
week
should
5, lecture 1, when it was started, it was mentioned.
No, there was nothing like that.
there cannot have been.
Can
So
It
are you
was
talking
not
about
there.
the
vertical line test to check if it's
Uh,
a function or not.
hmm.
So
Yes,
this
it was
passes
there
the
and horizontal
vertical line test.
Yeah,
for checking that if it is 1-to-1.
it's a function, but not one-to-one.
Yeah, so are you referring to some statement made by the prof, or was it in the instructor session, or would you clarify
The
where you
lectures that
read the
were
content?
posted on YouTube, the main lectures that we refer to.
Prof's lectures, right?
Yeah.
If you can give me a timestamp for when he says that in which video, then I would see it, try to clarify the confusion. But yeah, it's very highly unlikely, almost impossible that that statement has been made.
Okay.
Yeah.
I'll just put it in the chat box.
It's better if you let me know because I am on the other screen and I won't look at the chat.
Okay. Just give me a moment.
Yeah, that's fine. I would say towards the end of the session, when we are done with everything, you can go and check it and let me know. I can
Okay.
wait. Now you can
Yeah.
focus on what's going on here.
Yeah.
But this is a function. This is all right. You can, if you
Okay.
want to verify that using one of the tests we have drawn itself, you can just say vertical line test, and it's a function, right? This is a graph, and the vertical line test doesn't fail anywhere. Maybe you are referring to curve. If your curve is sometimes used for things without breaks and corners, but
Yeah,
function
it was
is
written in polynomial functions. They do not have sharp corners and they do not have any
polynomial
breaks.
function. Yeah, this is not a polynomial function.
Yeah, sorry.
So, oh, that's all. That's all. Okay, so right. Computing left hand and right hand limits is okay now, right? So this is very standard function. There are other ways in which the left hand limit, right hand limit may not exist at some point. You can just take maybe 1 by x. You take f of x is equal to 1 by why do I always do it on others? 1 by x not equal to 0, and 0 at x equal to 0. Let's define it on R. So does the left hand limit exist? Does the right hand limit exist?
No, sir.
At 0.
No, sir. It will be divergent to infinity
Yeah.
and
So at 0, if you look at the left hand limit, you're looking at points of this form. You're looking at sequences of this form, and you have the function values diverging to negative infinity.
LHL
And
and
if
RHL is becoming infinity.
yeah, there we'll just say the limit does not exist. It's actually blowing up to negative infinity for the left hand limit
Yes.
and positive infinity for the right hand limit. If you're looking at the right hand limit, you're looking at sequences of this form, and the corresponding function values will become arbitrarily larger and larger as you get closer and closer to 0. So this is one way in which LHL or RHL may not exist, or you can have oscillations also. I think this was also discussed. You can take a look at it again if you want. Things like x square sine 1 by x, or just sine 1 by x is also enough. 0. X square sin 1 by x will actually be good. So this. So over here, even though there is no blowing up behavior, this will always be between -1 and +1. There will be infinitely many oscillations as you get closer and closer. I'll not draw it. I cannot draw it properly. But if you want to see the graph, use any graphic software. And then look at the graph of this and check that at x equal to 0, LHL, RHL do not exist, despite them not blowing up to. So in this case, it is the oscillatory behavior that prevents the convergence. These are certain examples. Yeah.
Sorry to barge in. So I was not able to attend your previous sessions. I'm sorry for that. Given that now you are talking about the LHL and RHL where it goes on infinity minus, so where which it doesn't exist, is there a way? Is there a point also that they will converge?
If you include the extended real numbers, which is infinity and minus infinity, this will happen, but we don't consider that. So in this case, LHL RHL does not exist, means that the corresponding function sequences diverge. They do not converge. So for instance, if you
I'm sorry,
take
I think
this,
my internet is not stable. I'm sorry for that.
So if you consider the sequence for the computation of RHL of, let me call this F2, F3, RHL of F2 at x equal to 0. Let's take this for example. An is equal to 1 by n. This is a sequence which is greater than 0, which converges to 0. Look at what happens to f of an. F of an is 1 by x, right? And x is an, which is this, which is just f of an is n. Now the sequence n, does it converge or diverge? So if I take the sequence bn is equal to n, for instance, if f of n is convergent, is this a convergent sequence or a divergent or yeah, divergent?
Hello.
Yeah, is this a divergent sequence or a convergent sequence?
I think it become. I feel it's going on a convergence side, not on the divergent side.
It's a divergent because
It's
as we
divergent because yeah, go ahead, please. Explain.
because as we like increase the value of n, the value of bn will also increase to infinity.
Yeah, so there is no real number around which it gets closer and closer, right? Irrespective of what real number m you take, you will have all terms of the sequence much higher than this also. You will, whatever integers are there greater than m, it will go as far from m as you want. So you cannot have it converging at a particular real number m. So this sequence bn is equal to n is a divergent sequence, which means that there is a sequence greater than 0 converging to 0 such that the corresponding function values happen to be a divergent sequence, which means that this right hand limit does not exist. Similarly, you can do the argument for left hand limit by taking the sequence -1 by n. Is that fine? So I'll just use -1 by n, the sequence -1 by n. And for this, you use +1 by n. If you want to be even more clear with your argument. This is something you can use. And for this also, take it as an exercise or refer to, I think it was done in the Solve with a session, probably. We had done this in great detail. I refer you to that video. That is also available on YouTube.
I'll go through the session.
Okay. So I'll move ahead. Limits, properties of limits. These mimic the properties of sequences as one would expect, because limits are defined using sequences. So now that's not a proof of this fact, but it follows in the same fashion, and you have a similar sandwich lemma, which again, if you think about it graphically, if you have some function, doesn't matter how different the two are, close to a point if both of them approach the same thing, right? If you have something like this, and the limiting value is this, and if you have any function in between, that also has to approach that same value. So this is just sandwich lemma visually, but for problems you have to produce two functions, fx and gx, such that h of x is always in between these. And if you can do that, then okay, maybe I did the same mistake earlier also. This is f and this is g. Probably did a naming mistake while I was writing it for sequences also, but yeah, the idea is clear, I suppose. If, in fact, this need not happen everywhere, even in a small neighborhood around A, if it happens, then you're done. But if you get something globally also, it's fine. This is not a long step.
Sir, h of x should be bounded, right?
Near the point of interest, yes.
Okay. Okay, sir.
Because you can have things like, I mean, I can trivially make examples. I can just say, I can take three unbounded functions, and I can look at some point over here. I can take something like this, all of which are unbounded functions. And I'll say I'm looking at this point. I can't come up with an example immediately. Would polynomials work? Probably something like x square, x cube, x to the 4. But they will intersect. You can do that. It need not be globally bounded. That because why should this be bounded, right? It's just that it is in between f and g. The f and g could also go to infinity somewhere else. At A and near A, it will not. These all three will be bounded.
Okay.
Okay.
Okay, sir.
Yeah, maybe if I get an example later on, let's finish the syllabus. Now we have right-hand limit, left-hand limit. For right-hand limit, I look at the nature of the function to the right of it, and for the left-hand limit, I look at the nature of the function to the left of it. And if my function approaches the same value, as well as the function value being that same, being same as the two limits, then we say it is continuous. To understand it, we just say that there is no break in the graph. That is one way to look at it. Now if I have some function like this, which is linear, and then once again it is linear. There's no arrows on graphs, but only at this point. Let's say that is 1. I define it to be something like this. F of 1 is not equal to whatever this function seems to be approaching. In that case, there is still a jump. This is discontinuous. So if you want continuity, you will just see something like this. Like there is no break. So if you come from the right or from the left, you approach the same value, and that value happens to be exactly equal to the function value at that. So this is continuity. In terms of the language that we have already looked at, we say that the right-hand limit is equal to the left-hand limit is equal to the function value. So if you want to say that something is discontinuous, you can have this limit to not exist, or this limit to not exist, or for them to be not equal, or for them to be not equal to the function value. All of these ways. All right. That's it about continuity. Are there any doubts about continuity?
No, sir.
A common example of problem in this context is something where you are given two or more parts of the function. It'll typically be something like this. And you'll have an expression over here, you'll have an expression over here. And there will be some unknowns over here. And you will be asked to find the value of the unknown for which it is continuous. You want to take an example. Let's do 3 minus x plus I don't know. I don't know if this will even work, but 2 plus 3x. X plus b is enough.
And the function value.
Sorry.
We need to have the function value as well, I guess.
So here we have said x less than or equal to 2. So there it follows that.
Achha, okay, yeah.
Okay. So can you find the value of b for which it is continuous at 2? The domain may include some other point, but is there a value of b such that this function is continuous? And if yes, what is the value? If anyone gets the answer, please let us.
Sir, I'm getting the value as -8 plus minus 20 by 2. -8
Okay.
plus minus root under
Yeah.
20 by 2.
Okay, let's just not maybe go all the way with the solution because you'll get a quadratic equation. Let's just discuss the idea and move on. What is the left-hand limit? For the left-hand limit, you see that to the left of 2, the function is defined as b minus x divided by x plus b. So here, if I directly substitute the value, assuming that b is not equal to 2, I will get minus 1 divided by 2 plus b. The function value, because here it is written that
That should be
it is less
plus
than or
1,
equal
sir.
to 3 minus 2. Okay, yeah, that's plus. Yeah,
Plus 1.
sorry. This is also equal to this. On the other hand, the right-hand limit is limit as x goes to 2 of b plus 3x. Once again, this is a polynomial, so direct substitution works. So I'll just get b plus 6. So if I want these two, all three to be equal, these two are already equal. So all I need to worry about is 1 plus b by 2 is equal to 1 by b plus 2 is b plus 6. This is the same as b square plus 12b. Not 12b. We'll have what? 2b, 6b, 8b. 8b plus 12 minus 1 is 11 is equal to 0. Now, whatever are the roots of this, the discriminant doesn't seem to be very nice. So you can use the quadratic formula to get the value of this. You might encounter a scenario where this doesn't even have solutions. In that case, there is no value of b for which this function is continuous. So in the exams, if it has asked what is the value, then of course there will be a value. But there are scenarios where such things may fail to have equal limits. So is the idea clear?
Yes, sir.
All right. So now we'll leave continuity and we'll go to differentiability. Continuity will say that the graph doesn't have any breaks, but differentiability is for removing the corner points. Now, as was remarked earlier, polynomial functions they don't have breaks or corners. But the more general class of functions which do not have breaks or corners are differentiable functions. And we'll define differentiability at a point, once again, using limit of a function. But that function is not just the function that we start out with, but we look at the rate of change of the function with respect to the input variable, and the limiting value of that is called the derivative at x. So this is a. This is also a. So what's happening? You're looking at the change in the function, which is when I go from a to a plus h, what is the change that happens? I'm looking at that, and that has happened in time h, right? So this change in output divided by change in input, I'm taking the ratio of that, and then I'm taking points closer and closer to a. So the limiting value of that rate of change is what is called the derivative. Common notations are f prime x d by dx. Differentiable functions are always continuous, but there are continuous functions which are not differentiable. Can you give me an example of a continuous function which is not differentiable?
Mod of x.
Yeah, modulus function is continuous but not differentiable. Anything that has columns. So this function for this function, for the float function, do you need to check whether this is differentiable by computing the limit of f of x plus h minus f of x divided by h? So is the float function differentiable? Is the question.
It's not continuous, so we can conclude that it is not differentiable.
Yeah. So here what I've written is differentiable implies continuous. This is equivalent to saying not continuous implies not differentiable. Okay. Properties of derivatives. Sum and scalar multiple properties are straightforward. Straightforward in the sense that the derivative of the sum function is the sum of the derivative functions, and scalar multiple also just comes out. But for product and quotient, you have a different formulation. But by now, I think you have seen enough of differentiation, rules of differentiation, that you know this by now, f prime x gx plus f g prime. And the quotient rule. The chain rule is something that also you have seen in practice for things like sine 2x. What would you do? You first differentiate the outside function, which is f prime of gx, is what you're doing. Cos of 2x. 2x is the g. F is sine. So f prime of g of x times, you're going to differentiate what is inside, which is just 2. So this is a very basic example of the chain rule. So that's how you differentiate the composite function. So can you quickly tell me what is, suppose I have a function which is invertible, meaning it's an injective function and I can define its inverse on the range. And it happens that inverse also is differentiable. So in that case, what would be the derivative of the inverse?
Come again.
So will that be the derivative of will that be the inverse of the derivative of f of x?
Yeah, but derivative need not be invertible even. That's not correct.
Okay.
So the hint is that you have to use this.
Okay. So we can apply that like FOF of x equal to x, right?
If you could kindly
Yes.
repeat the question.
Okay, sir.
So let's make it on a different page itself. I'll write the question clearly. So suppose f is n. I'm going to write invertible function. This terminology you may not have seen. If you have not seen that, it is just a one-to-one function. Let's just call it a one-to-one function. The inverse exists is what invertible means. Invertible function such that f inverse is also differentiable. Then what is the derivative of the inverse function? Of course, you'll have to write it in terms of the derivative of the original function. So if I look at this composition, what is this equal to?
This is X only.
F of inverse is
So if I start out with something in the range, I go to F inverse, I come back, I'll land in the same thing. So F of F inverse or F inverse of F, both are equal to X. Now, if I take the derivative of this,
It would be 1.
this is 1. On the other side, the derivative is 1. This I can use the chain rule. I can say it's F prime at F inverse of X times F inverse prime X. So F inverse prime of X is 1 by F prime at F inverse X. Okay.
Yes, sir.
If you want to see some explicit example instead of just arbitrary functions, F of X is equal to e to the X. What is F inverse of X?
Same.
F
E to
inverse
the
is
power.
not.
Oh, okay.
No,
Okay.
what
So
is,
it would be ln of X, ln X.
yeah, the natural logarithm function. That is the inverse. Now, F inverse prime of X, the derivative of log X, I know it is 1 by X, but suppose we don't know. What if I use this? So here F prime X, suppose I know F prime X is equal to e to the X, but I don't know the derivative of log X. I want to derive the derivative of log X. So F prime X is e to the X. So F prime F inverse of X, what is that? That is F prime at log X. So that is nothing but e to the log X, right?
Yes, sir. Which is X.
Which is X. So this thing is just X. So I'll just write it as 1 by X. So this is a very quick proof of why the derivative of log X is 1 by X, but there are things going on in the background. You should know what the derivative of e to the X is, and then that log is actually differentiable and all that. But yeah, this is just one application. All right, so that is the derivative of this. And one of the last things in the computation of L'Hopital, and one which is practical and comes up in many problems, is when you have functions of the form f by g. Okay, here I've written f1 by f2. There are some conditions which need to be verified in order to apply it, which are explicitly written down in the prof's videos. You have please go through those conditions. Most of the time, you will be given questions which obey those conditions as far as the exam is concerned. But the basic check that you have to do is if the limit of the numerator and denominator, when you compute them, is it in the form 0 by 0 or infinity by infinity? Something like log x would go to infinity, and something else that would go to infinity. Let's just say e to the x. But that would also go to infinity. This would also go to infinity. This is okay. But this you can't solve. So let's just take x log x. I think we have already seen this. But let's do this again. So x log x is actually not in f1 by f2 form, but I can convert this to f1 by f2 form by just doing this. Right, this goes to infinity. This also goes to infinity. So I can apply L'Hopital's rule where I compute the derivative of the numerator and the denominator separately. I'll write this as 1 by x and minus 1 by x square. This is equal to minus x, and that has a limit as x goes to. Okay, here we are talking about x goes to 0. So this goes to minus infinity and this goes to infinity. 0 from the right. So this is one application, but I'm sure you'll find many problems of the form. So if I have the function to be f1 by f2, where both f1 and f2 go to 0, or both f1 and f2 go to infinity, what I can do is take the derivative of the numerator and the denominator separately, take the ratio of those, and if the limit of f1 prime by f2 prime as x approaches to a exists, then that limit is equal to the limit of f1 by f2. This is L'Hopital's rule. For example, you can do this. This is better. So limit as x goes to 0. So what form is this in, this limit?
0 by 0.
So log 1 is 0. So your numerator approaches 0 and the denominator also goes to 0. So this is in 0 by 0 form. So you can apply L'Hopital's rule. So if I take the derivatives, what I get is f1 prime by f2 prime is this. And as we approach 0, what does this approach?
1.
So this limit is 1. So that's an easy exercise. Now, if I have something like 0 by infinity form, say 1 by e to the x, just something like this. Limit as, okay, here I'm taking x goes to infinity. You can do this also. This is fine. X goes to 0 plus. In this case, you can't apply it. This limit actually is equal to what?
Is this, sir, is this going to be 0?
This should be 0.
Yes, sir.
Why? Because here this is becoming as large as you want. The numerator is staying the same, but the denominator is blowing up. So if you have infinity in the denominator, sorry, yeah, infinity in the denominator. Just one moment. Okay, yeah, sorry about it. If you have infinity in the denominator and a finite value in the numerator, then your limit is 0. So if you have something like c by infinity, that will go to 0 always. That will go to 0. And if you have something like c by 0, then that will go to infinity. The limit will not exist. So you have to make sure that this is in 0 by 0 or infinity by infinity. One more way to see that this actually goes to 0 is you can write this as log 1 by log x, which you can write as log 1 minus x. So that also works.
Okay, sir. Sir, in that question, like x into ln x.
Yeah.
So, like, if we like, if I don't want to use the L'Hopital rule, then is there any alternate way to find the limit?
Not that I can think of directly. And not within whatever has been taught in the course.
Yes, sir. I mean, with the help of expansion, we can do this, right?
Yeah, as in you're talking about Taylor series, is it?
Yes, sir. This expansion of ln x, we can consider that.
Expansion meaning? You're talking about the Taylor series only.
No, sir, I have not heard about that. Like,
Oh, okay, sorry.
in
Yeah.
11th, 12th, like the way we studied expansion of log x and that x by some x factorial, those kind of things.
Yeah. That is the Taylor series of log. So
Oh.
yeah, if you like extra reading, if you want, you can do using Taylor series. Every analytic function has something called a Taylor series expansion.
Sir, every term, right?
Every analytic function has something like that. So e to the
So,
x,
was this taught?
has this.
Did I miss something in the lecture? Was this
No,
taught?
no. So this is completely not in the syllabus, and you can just if for the course you'll not be needing this.
So we can
Since he was
focus on the
interested.
course portion first.
Yep.
I think.
Yes. So this is something that has been covered. So I'll just tell you, it's something like this, right?
Yes, sir. Yes, sir. Exactly.
I might be missing some term there. So even logarithmic function has some series like this, some series representation like this. If you can use it, but then you'll have to talk about limits of those series and all that, and that is not part of the syllabus. So I'll skip it, and it is
Okay.
easy enough to do with L'Hopital's rule. So let's be
Okay,
content
sir.
with
Yes.
that. Okay. And the last topic, second last, but last practically, is the equation of tangent line. So one more thing that the derivative of a differentiable function gives is that the value of the derivative at a point x is actually slope of the graph at x. Slope of the line, slope of the tangent line to the graph at x. Now, if the derivative is slope, I'm looking at this point, right? What is this point? What are the coordinates of this point?
X comma f of x.
X comma f of x. So I have a point x comma f of x, or in this case, I've written it as a comma f of a. So let me make that change. This is a point, and the slope is given by the derivative at that point, f prime at a. Using the point and the slope, I can get the equation of the line in the point slope form. That is one more way to remember it. Even if you forget this equation, y is equal to y naught plus m times x minus x naught. This is the slope point form of the straight line, or the equation of the straight line. And very quickly you can see that a comma f of a is a point, and f prime a. If you remember that f prime a also happens to be the slope, then you can derive the equation of the tangent line as well. All right, so this is the equation of the tangent line. And similar function that any tangent line will be a function, right? So anywhere you draw the vertical, every straight line in the plane except the vertical straight line itself will be a function, and that function happens to be the best linear approximation of the function around that point. Meaning, if I look very close to the point, the values of the function and that straight line will be the same. As you move away, there might be a significant difference, but near that point, the value of this function, f of a plus f prime a times x minus a, as well as f of x, will be close. And what close means, you'll have to define depending on the case that you're considering. That is once again not part of the course. It will probably come later in later courses. But for now, you should just know how to compute the best linear approximation. And that is just done by using this formula, which is identical to the equation of the line, which can be derived easily using the point slope form. That brings us to the end, and we have already overshot. So problems, you can take it up in the TA session, or you can put it up on discourse. We'll discuss there. If you have specific problems already, you can speak up now. I can take a couple of them. Otherwise, we'll wrap it.
Sir, is there any more revision session?
Not any instructor session. I don't know about TA sessions. I can ask and let you know.
Okay, sir.
I mean, you must have the schedule.
Okay, sir.
So, will we be having the evacuation session in the live course, live sessions?
Just one moment. No, instructor sessions won't be there. There will be one session for there was already a TA session today, right? 4 to 6.
It was there.
Yeah, so there is one more TA session tomorrow. The particular agenda I'm not aware of, whether it is PYQ or problems or what. There will be one more mock discussion session. I don't know when the dates exactly are, but this should be communicated to you or should be available in the calendar at least.
Yeah, but for quiz one, actually, we had a split of two instructor session. So I don't know which was because of some reason it was planned or nothing, but for quiz two, we have only one. So I was also checking the calendar whether we have another session apart from today.
No, instructor revision session, there's only one. I was told to take this one and cover all the topics. So yeah, that's what I have done.
Okay, thank you.
Sir, then I have some doubts related to asymptote. So,
Is it doubts which are, is it terms discussed in the course?
sir, asymptote, horizontal, vertical asymptote was there in the syllabus. I have not any doubt on any specific question. I just want to
Okay.
know what is the mathematical approach to find the asymptote.
Find the asymptote?
Yes, sir.
I don't think this is discussed anywhere.
It is there in the course, and some questions were also there.
In which week content was asymptotes discussed?
So week 5, 6, exponential and logarithmic function.
I think
Sir,
there it is specifically for exponential and logarithmic. I think it is said that this is the asymptote.
yes, sir, exactly. For
The y-axis is the asymptote for the logarithmic function and this.
yes,
But
sir.
in the general method is not discussed. Right?
Yes, sir. But in some questions are based on that asymptote. Like for the simple, if you take a to the power x, then we can say that like the horizontal asymptote will be just the x-axis.
Yes.
But if we'll be getting something which is not in the form of a to the power x only, a to the power some function, let's say given.
You will not get things like that. No.
Okay. If if in the exam asymptote won't be there, then it is okay. Just like
Yeah, it won't be there in the exam.
okay. Okay, sir.
Yeah.
Okay, sir. Thank you for the session.
Sir, can you share this note, sir?
This will be there in the same sheet as
I am first
usually.
time. I am first time coming.
Okay. So you can go to the portal, and after the weekly content, there's supplementary contents, and within there is live session slides.
Okay.
Yeah. There you can get the slides for all weeks. Whatever we have uploaded so far. And I'll be uploading just after the session. I'll be uploading this there as well.
Okay.
And but take care that there are certain things which I have not written out in full detail. For example, L'Hopital's rule. There are other conditions that need to be verified. I've just written the essence of things. Be careful that your primary source of reference is the prof's videos always. And there are some typos also over here. Please make sure that you don't take this as absolute truth. There might be typos and some see, okay, here I have actually defined in an interval around A. Sometimes I might skip that because it's a subtler point which is not so relevant in problem solving. Okay, just be careful about it.
Okay.
All right, then. I think we'll stop for today. All the best for the quiz.
Thank you, sir.
Thank you, sir.
So the document would be uploaded in the calendar link.
No, it'll be there in the supplementary content
Okay.
live session slides sheet.
Thank you.
Okay.